In the previous video, we introduced floor problem. We talked about naive solution and efficient solution. Let us now talk about C++ implementation of the efficient solution. We are following the same idea. We begin with the root. We follow like normal BST search. If the root itself is same as key, we return the root. If the root is greater, it means that floor has to lie in the left subtree. If root is smaller, then root itself can be a potential floor and the floor can also be in the right subtree. That's the same idea we are following. So we've written a function here. This function returns null if there is no floor present. For example, if you're finding floor of something like 10 in this BST, then this function is going to return null. Otherwise, it's going to return a floor address of the node which has the floor. For example, if you are searching for floor of 58, it's going to give you the address of this node. If you're searching for floor of 45, it's going to give you the address of this node. If you're searching for floor of 30, it's going to give you address of this node. Let's see how does this work. We initialize our result as null. We do begin search with the root itself. And then we say while root is not equal to null, while we do not hit a leaf node, while we are searching across the height, we keep searching. If we find the root arrow key is equal to x, we return root. If the root arrow key is greater, we go to the left side. If it is smaller, then we update the result as root and we go to the right side. Let's do a dry run for 58. Let's say we want to find out floor of 58. We'll begin with here. We'll go to the case where we have root arrow key smaller than 58. So we'll make the result as root. So our result now has address of this node 50, right? And now what we do, we go to the right side. And this side, when you go, you see that root is greater than the search key, right? Search key is 58. So what you do, you go to the left of it. You go into this case and you go to the left side. So let me write down here, the search key is 58, right? So we begin from here. We initialize this result as 50 because this was smaller. Now we come here, it is greater. So we go to the left side. And when we go to the left side, we again see it is greater. So we are going to the left side again. And now we are going to update the result, right? We'll come here and update the result as address of 55. And now where are we going to go? Left or right? 55 is smaller than 58. So we'll go to the right side. But when we go to the right side, we find a null. So we come out of the loop and whatever result we have, we return it. So we return 55. Let's do one more dry run for 35. Say I want to find out the floor of 35. I'll begin with root. I'll see that it is greater. So I'll go to the left side. I'll come here. It's a smaller. So I'll go to the right side. But before going to the right side, I'll update the result as address of this node, right? So my result is currently address of 30. Now I come to right side. I come to 40 and I see 40 is greater. So I'll go to the left side and left side is null. So I come out of the loop and my result remains 30. So we find the floor as 30 in this example. Now what is the time complexity of it? We are traversing across the height. So it's big O of h. And how much auxiliary space it requires? We are not using any array or any recursion called stacks. So it's big O of 1 extra space.